All right, so hi everyone. Today we're happy to have Ofri Telem from HUJI, who will tell us about bound-unbound universality and the all-order semi-classical wave function in Schwarzschild. So please, Omri.
All right. Thank you so much for the invitation. It's a pleasure to speak here. And I'm going to tell you about one paper in kind of a largest research direction that I've embarked on in the past 3 years or so. A lot of it is spearheaded by my excellent student Majid Khalaf, who's here in the audience. Whenever there's a really tough computation, you know that he did it. So the context of this work is extreme mass ratio black hole in spirals. And this is a video that was in Scott Hughes' talk a few weeks ago. He put it with sound, which in my opinion was unbearable, so I just put it on silent. And you can see that this in the center, there's a supermassive black hole, and this is basically the trajectory of a small solar scale black hole spiraling into it, emitting gravitational waves, and kind of going inwards until it merges with the big black hole. And in this context, I'm going to write the overall mission of our research, which is to compute analytically both the trajectory of the inspiraling black hole and the gravitational wave that comes out of it. Okay, so we want to compute the source trajectory, which is a point in four-dimensional space-time as a function of the proper time of the motion. We want to compute the source energy momentum tensor just from this moving mass on a trajectory. And of course, we want to compute the emitted gravitational wave, which varies schematically and only to leading order in the mass ratio of between the large black hole and the small black hole can be written using the Green's function method as an integral of basically the source, which is something that has to do with what emitted the wave, and the retarded Green's function, which is a characteristic of the gravitational fluctuations, the gravitational wave, in the ambient Schwarzschild background. So we can talk about current and the future, but right now we're talking about Schwarzschild. Okay. Now, for people that are not in the field, this might seem like, it's hard to gauge the hardness of or the difficulty of this task. So let me assure you that this is a very hard task, to the point that I don't think there are a lot of people out there that actually are trying to compute this analytically. And most of the work is semi-numerical, meaning that you can write Green's functions and you can write sources, but down the line, it all comes down to numerical integrals, which we don't want to do. So we want to do everything purely analytically. So the question is, why do we just like pain and suffering? So the answer is, it's not just that. It's that we eventually want to use it to greatly improve on the existing cutting edge codes at the second order in the mass ratio, in which are in dire need of some resummation, some sum over multiples of angular momentum, which is a huge computational problem. And when you want to resum something that you compute only numerically, basically good luck with that. It's basically impossible. So the hope is that knowing and understanding the actual functional form of the gravitational waves that come out at first order would enable us to have a game-changing contribution at second order. But that's kind of a motivation for the future. And another motivation is that there's a huge body of work in recent years, maybe the past 5-6 years, to compute gravitational scattering in post-Minkowskian perturbation theory. And we would like to compare this to the different regime of extreme mass ratio in spirals, in which you kind of expand around geodesic motion. So these are two vastly different approaches to a similar problem. One is basically scattering massive objects in flat space. The other is looking at geodesic motion of a small object in the background of the Schwarzschild background of a large object. And the question is, how do you connect the two? So there have been comparisons that were numerical, but we actually want to touch base analytically. So that's our motivation for the hard task that we took upon ourselves. So the overarching goal of our research program is to compute the gravitational radiation reaction force in black hole extreme mass ratio in spirals analytically to a desired order in the coupling in G Newton, and at first order in the mass ratio, and then eventually at second order in the mass ratio, which is today's state of the art, and use it to generate predictions for future waveforms that will be measured in the LISA space interferometer. So like I said, using existing methods, this task seems very hard to impossible. And if you want to compute it at order G to the n, it's in a way equivalent to a huge set of n-1 loop computations in terms of, for example, Feynman diagrams of scattering in GR, in linearized GR. Now, with the quantum spectral method, which is the name that we chose for our method, and I'll explain to you shortly why, this becomes possible. It may be the result of a lot of hard work, but it is possible. Okay, so what's the quantum spectral method, and why do we call it quantum? Because this is classical GR. Why the hell would we use the word quantum in this context? So the quantum spectral method is a framework to analytically compute all time-dependent observables for any relativistic conservative motion. So when I say conservative motion, I mean, for example, a geodesic motion in Schwarzschild in a spherically symmetric potential, okay? Now, this is the modest goal, okay? Because eventually we want to compute an in-spiral, a trajectory which has gravitational back reaction. So one may ask, why is it important that we want to compute the radiation emitted by an object on a geodesic object? Well, the answer is that this is a module in a perturbative calculation which takes into account the gravitational back reaction. So first things first, we want to be able to compute geodesic trajectories analytically, the entire time-dependent motion analytically. We want to compute the radiation emitted by a small black hole on a geodesic, on a conservative trajectory. And we want, from the emitted radiation, to compute the back reaction at leading order. So at leading order, you assume that the source that emitted the gravitational waves is geodesic. It emits gravitational waves, and they take energy and angular momentum from your object, which leads to it deviating from its geodesic trajectory and going in. Now, let me comment on the word quantum. So the word quantum is kind of a charged word. So I want to, right off the bat, explain what I mean by quantum. We're not quantizing anything. This is also, we are doing it in the relativistic limit. So if we wanted to do a proper quantization, we'd have to do quantum field theory. And that's not what we're doing here, okay? So when I say quantization, it's in a very limited sense. It's the idea that we start from, instead of solving for point particle motion, we basically solve the Klein-Gordon equation for some scalar field in the background of the large black hole. Now, in the actual problem, there's no scalar field, right? There's a point particle. But the point is that the movement of any point particle is somehow locked or hidden inside the WKB limit of the field equations. So fields become point particles in the limit, in the WQB limit, which in optics, you would call it the geometric optics limit. Okay, so it's exactly the limit where electromagnetic waves become light rays that trace their conservative trajectories. So when I say quantum, it's basically a classical field equation, which reduces to point particle motion in the WKB limit. And like I said, though the computation is associated with conservative trajectories, it can be used as a module in post-adiabatic perturbation theory, which is something that Scott Hughes greatly touched upon in his conversation. So I'm going to set it aside and focus on the limited problem of analytically computing things on a geodesic orbit, and that can be used later for describing back reaction as well. Okay, so in this talk, I'm going to talk about a surprising universality between bound and unbound motion. Okay, so for Keplerian orbits, we have this naive notion that for a bound orbit, we have motion on an ellipse, and for unbound, we have motion on a hyperbola. And somehow there's a trivial analytic continuation between an ellipse and a hyperbola. Okay, for positive and negative energy, basically. So I'm going to show you that this notion is very deep and it actually holds almost for any system. And it's computable. So we can, any observable of a system, we can compute in an analytic form, which is manifestly amenable to analytically continuing between bound and unbound orbits. Okay. And this, depending on your intuition, this may or may not make sense to you, right? If I have like a point moving on an ellipse in a certain varying pace, can I necessarily map it to a point moving on a hyperbola? I don't know, but turns out that you can actually do this, and I will show you how. I'll present the quantum spectral method and a sketch of its proof using the geometric optics or the WKB method. Then I'll show some results, a taste of how to do an actual computation, and basically how we computed anything you ever wanted to know about relativistic Keplerian motion and the emitted field from it. And then I'll show you how the Keplerian computation is not just an illustration of how the method is used, it's actually the fundamental building block that we will use to eventually compute Schwarzschild. What I'm not going to show you, because there's just too much, is a cross-check with post-Minkowskian methods of the emitted field in the context of an electromagnetic example. I will not show you how to get the fundamental frequencies of Keplerian and Schwarzschild from Bohr-Sommerfeld quantization, even though it's something that I really like. So maybe you can ask me about it in the questions. I will not show you how the emission of electromagnetic waves can be computed as just the h bar goes to zero limit of spontaneous emission in the hydrogen atom. And I will not show you how we computed an electromagnetic adiabatic in spiral. But all these things are in the 100 backup slides that I have, so please ask if you want. What we don't have yet is the actual computation of radiation reaction in Schwarzschild. We don't have yet a generalization to Kerr, and we are thinking about applications away from the probe limit. Okay, so not in the sense of an object moving in an ambient metric, but more in the sense of LIGO, of similar mass black holes. But these are things that are really in the works, and it's better not to dwell into them too much right now. Okay, so let's get right to it. Yes.
When you discuss the fundamental frequencies, these are the fundamental frequencies of the motion, of the Keplerian motion, for example.
Yeah, exactly. So for for non-relativistic Keplerian, you only have one, but for relativistic, you have precession, right? You have a periastron advance, and there's a beautiful, well, I don't want to get dragged into it, but if you take the difference between two energies of the hydrogen atom, and you take the classical limit, you just get the fundamental frequency. So if there's time, I'd love to show you.
In the Icona limit, though, or?
In the h bar goes to zero limit. So you literally take the energy of the hydrogen atom, one minus the other over h bar. You take this limit, you get the radial frequency of Keplerian motion, like Kepler's third law. Yes. So, okay. So remind me to show this after the talk. Okay. Okay, so let's start with a refresher on relativistic motion in a spherically symmetric potential. I say a refresher, though maybe not everybody saw this, and I'm definitely not going to derive all these things because this is going to take too much time. But I have a relativistic point particle with a certain mass mu and energy, conserved energy E, and an angular momentum in the z direction. And because the potential is spherically symmetric, then without loss of generality, the motion is in the xy plane. and the angular momentum stays in the z direction. And I can write down relativistic equations of motion using my favorite method. I can just write Newton's laws with the relativistic correction, or I can use the Hamilton's equations or Hamilton-Jacobi. And basically what I get is an equation for the time derivative of position, the time derivative of the azimuthal angle within the xy plane, and the derivative of time with respect to proper time, which is the Lorentz boost. And now, of course, as the body encircles, okay, does this, precessing motion, its velocity changes, so its Lorentz boost changes. It's not a constant, it's a function of radius. And so what's system specific here? It's the effective potential, V effective, that you are in, and it's also the boost as a function of where you are on the trajectory. For example, if I'm an electric point charge and I move in a Coulomb background, where K is basically alpha QQ, the effective potential, okay, is going to have the familiar 1 over r term, but also because it's relativistic, there's going to be a correction to the angular momentum, which goes like minus k squared over r squared. And there's also going to be a change in boost. So the boost is going to be r dependent. And this can be trivially derived from the Hamilton-Jacobi equation for a relativistic charge, classical charge moving in a Coulomb potential. Now, we know very well that we can have bound motion and unbound motion. And in the relativistic setup, it's basically a question of whether the energy of the trajectory is more or less than the rest mass of the body. Okay, so when it's more, you're basically above, you're in an unbound trajectory. So you just go once and you go back to infinity, and the motion is between r minimum and infinity. While if the energy of the trajectory is smaller than the rest mass, then you get this bound precessing motion. And by the way, I'll get back to this, but these are exact analytic computations of the shape of these trajectories for Schwarzschild. So this is not numerics. These are elliptic integrals kind of under the hood here. Okay. So a few relevant quantities for later. We can define the Hamilton-Jacobi function, which is this integral from the turning point radius up to a certain r of the square root of u. We have the radial action, which is basically the Hamilton-Jacobi function. If you're in bound motion, it's basically the integral between the two turning point radii, between r min and r star, which is the maximal radius for bound motion. I can compute the radial period. This is what will give me the Keplerian period of the system. And 2 pi over the Keplerian period is the frequency. That's the fundamental radial frequency of the system. And I always want to work with real positive quantities. So for bound motion, this omega b is going to be positive and real. But for unbound motion, because there's a square root of e squared minus mu squared, if I go for unbound, it's the omega, which is, there's an I factor here, which becomes real and positive. So this may seem like details, but this is actually the crucial point about analytically continuing between bound and unbound. So this will come back in 2 slides, big time. And just for later, we can compute the periastron advance, which is given by this. This is the precession, okay, because of a special relativistic effect. Okay, good. So let's go to time-dependent observable. So consider a time-dependent observable O of t. This is a generic name that could correspond to the radius as a function of t, the azimuthal angle, the emitted field, etc., etc. Clearly, this is very different between unbound and bound, right? Radius goes to infinity for unbound. It oscillates between 2 radii for bound. So the question is, why the hell would I have an analytic form that kind of connects between the two? And it turns out that you can actually find one. And this is a crucial question for the computation of bound black hole in spirals, with unbound scattering amplitude methods, because all us particle physicists, we want to compute, two black holes circling each other. Okay, but what we know is how to scatter particles that go to infinity. So we always work in the unbound limit, and we want to somehow analytically continue to bound. So this is a crucial question, so that all of our efforts won't be, gone to waste when we want to compute the bound system. Okay, so here's the answer. What should you compute in order to naturally go from bound to unbound and back? And the answer is you should compute the Laplace transform of your observable. Okay, and I'll explain why. Okay, so the Laplace transform, as we learn in maybe first year in university, is given by this integral. It's almost like a Fourier transform, just without an I. And there's also an inverse Laplace transform, which takes us from the Laplace observable back to the time-dependent observable. In this talk, we will use the QSM to show how to actually compute Laplace observables in a radically new way by extrapolating from field equations. But let's, for 1 second, assume that somebody just handed to us the O of SL. So this is the representation of the operator O that we're interested in Laplace space. What can we do with this? The answer is that it trivializes the continuation between bound and unbound trajectories. The reason is that in the bound regime, okay, there's this I between the two fundamental frequencies, which I kind of was emphasizing earlier. So this I turns the Laplace transform into a Fourier transform, which is what we need to describe bound motion. And in particular, we can compute the inverse Fourier transform with a contour integral, like I'm showing here. We can compute this by closing a contour in the bottom half plane. And basically, by Cauchy's theorem, what we're doing is we're picking up all the poles on the real axis of this Laplace observable. Okay, this is what turns the Fourier transform, or an inverse Fourier transform more precisely, into a Fourier series. Okay, so that's the secret of how to analytically continue a trajectory that just goes to infinity to a trajectory which is periodic and oscillates between Rmin and Rmax. The inverse Laplace transform becomes a Fourier series, which just sums over and reconstructs a periodic observable in the bound limit. Okay, so the bottom line is, if somebody handed to me the complex function O of SL, the Laplace representation of the operator, I'm going to trivially be able to compute all bound motion and all unbound motion, no problem. Okay, so the problem is now finding how to compute these Laplace observables. Now, there's one particularly cute Laplace observable that we can compute using methods known for about 100 years, and that's the radius in relativistic Keplerian motion. And this is the result. So you don't need our methods to compute it. You can open some book of like celestial motion, and a variant of this formula would exist there. Okay, so it looks fancy, but it's a derivative of a Bessel function. That's all that there is here. And now we can use this, substitute it in the inverse Laplace transform for unbound trajectories, and get unbound motion as a function of time. Alternatively, in the bound regime, where the energy is smaller than the mass, okay, we substituted in the inverse in the Fourier series, the inverse Fourier transform, and we get this periodic motion. Okay, so essentially, if you can find the Laplace observable, the analytical continuation between bound and unbound is a solved problem. And before I continue, let me ask if there are any questions.
So I actually have a question. So you were saying that the poles are on the real axis, and that's, I guess, is related to the fact that you're considering a conservative, only the conservative problem. So, I mean, I don't know if there are other obstacles to do that, but in principle, could you also consider the non-conservative problem? And then these poles will shift a little bit from the real axis.
The answer is yes. The answer is that I myself was a conservative in the colloquial sense, right? And I only wanted to think about the extreme mass ratio problem in which you don't have the problem. You can compute like post-adiabatic perturbation theory by just focusing on the radiation from a conservative and oscillating geodesic. But recently, I've been told that our method could apply away from the probe limit. So I'm very excited about it, and I want to think about it. The answer. Good. So why don't I continue? All right. So let me tell you how to compute Laplace observables, right? So that's the essence of our method. The idea is that you, like I mentioned before, you start from a classical field equation and you take the WKB or geometric optics limit to reproduce the point particle motion. So we have an observation that the motion of a spinless point particle in a spherically symmetric potential is somehow encoded in the WKB limit of the Klein-Gordon equation in that potential. And I'll explain why this happens. So the Klein-Gordon equation, specifically, let's talk about relativistic Coulomb. So eta mu nu here is just Minkowski, and A mu, the vector part is 0. The A0 is just a Coulomb charge. So this is just a point Coulomb charge in Minkowski space. And note that I put mu here over h bar squared. So in particle physics, we usually take h bar to 1, but here we want to use h bar as a control parameter. And you see that the units actually fit. So h bar has to be here in order for the units to fit. And we can use h bar as a control parameter. Okay. So when we take h bar to 0 while taking the angular quantum numbers or all the quantum numbers to infinity, what we're going to get is an infinite frequency solution. And that infinite frequency solution, it's basically the WKB solution to this Klein-Gordon equation, is going to encode the classical behavior of a point particle. In other words, I could just solve this problem. It's very similar to how you solve the hydrogen atom. And the solutions are exactly hydrogen orbitals, okay, with some boosts spread here and there. And in the WKB limit, which is the limit in which the control parameter h bar goes to 0, this wave function becomes more and more and more like a sine, okay, of a quantity SR over h bar. Now, the SR is the same letter that I denoted the classical Hamilton-Jacobi function of the system. And this is not a coincidence because it's actually that, okay? So that's how classical behavior emerges from or point particle behavior emerges as a limit of a field equation, okay? It comes inside the sign and it's divided by h bar. So the hope is that we could compute matrix elements over these field solutions and then later take h bar to 0 and reproduce the meaningful quantity for point particle scattering, which is indeed the case. To do that, we define what we call a wave function, quote unquote. It's not really a wave function in the sense that there's no quantum mechanics. It's a solution for a classical field equation, but it's nice to kind of use the quantum notation here because it eases the intuition a little bit. And there are various quantities that we may need later, like the energy, the asymptotic velocity, if you're in a scattering orbit, the wave number, and the Lorentz boost. So these are just formulas, and I don't want to dwell over them too much. And the idea now is that we can define matrix elements. Matrix elements are exactly like in the hydrogen atom. It's a sandwich of an operator between a bra and a ket, and it's defined as the integral of the operator as a function of r, theta, and phi, sandwiched between the bra wave function and the ket wave function, exactly like in the hydrogen atom. And we chose the prefactor defining this quote-unquote wave function very carefully, such that there's actually a meaningful point particle limit to these matrix elements, which I'm going to show right now. So if there's anything to remember from this talk, it's going to be the following equation, and we called it appropriately so the master equation. This is what allows us to do everything here, right? So you may remember that the object on the left is the goal. This is what we need. It's the Laplace representation of an operator, which enables us to compute the time-dependent quantity, both in bound and in unbound. On the other side, there's the classical limit, or the point particle limit, when h bar goes to 0 limit, of a quantum, quote unquote, matrix element between Klein-Gordon wave functions. Okay. In the non-relativistic limit, it's like saying that we can compute matrix elements over the hydrogen atom and reproduce everything about Keplerian motion, which is what we actually did in our first paper. So in the point particle limit, the quantum numbers on both sides, on both the bra and the ket, go to infinity, as they should, while their products with h bar are finite, and they're the dimensionful action variables for point particle motion. Okay, so JR, L, and M, lowercase, go to infinity, h bar goes to 0, but their product becomes JR. JR is the actual action variable of Keplerian motion, or of the classical motion. L is literally the angular momentum, the classical angular momentum. LZ is the z direction angular momentum. Now, the important thing here is that the quantum numbers of both sides, both the bra and the ket, go to infinity, but their difference remains finite. And it's, in fact, proportional to SL, which is the variable of the Laplace observable. Okay, so somehow I need to reconstruct the function of this SL. So it appears on the left-hand side, it has to appear on the right-hand side too, and it basically characterizes the difference between the bra and the ket as you take the classical limit where all the quantum numbers go to infinity. Why would that be true? It looks like kind of a wacky formula. So the idea is that you can prove it with WKB very easily. You actually compute this matrix element, and instead of the functions, the full functions, you substitute their WKB, and you see that you can massage it a little until you reach the exact definition of the Laplace transform that gave you O of SL to begin with. Let me give you a little sketch of this proof. So I want to prove this equation. The first thing I'm going to do a multiple expansion of this operator. And now I'm going to substitute this, this expansion, substitute the formulae for the wave functions in their WKB limit, do some angular integrations. I'm not getting into the fine details on purpose because it's a waste of time. But what happens is that what you're basically reproducing is that there's an integral here over R with an e to the I over h bar, the difference between the Hamilton-Jacobi action associated with the non-prime quantum numbers and the one associated with the prime quantum numbers. Okay, so somehow we said that the difference between the two is characterized by the Laplace variable SL. So somehow you're step-by-step reconstructing the definition of a Laplace transform here. So let's go to the next step. Okay, to take the limit of h bar goes to 0, I take partials of the action, which I can then compute. You see that there's a dr over r dot here, so I can change integration variables to an integration over t. And now we're in the game because it's really starting to look like a Laplace transform. And we remember the definition of the relation between delta JR and SL, which I glossed over a little bit. And you reach the exact definition of a Laplace transform. So if this went over your head, that's fine. I kind of put it out there so you can, if you're interested, you can look at the slides later or the paper and reproduce it step by step. But the main takeaway from the slide would be that proving this is rather trivial. It's just using WKB. You just do WKB like you would do in undergrad quantum mechanics, and you just reproduce the definition of a Laplace transform. Okay, what is it good for? So we can use it to compute any observable for relativistic Keplerian motion in a manifestly bound-unbound way and to all orders in the coupling. So if you compare it to like post-Minkowski or in the context of electromagnetism, post-Lorentz computations, This is like a resummation of all Feynman diagrams at all orders, at all loop orders. Okay, this is in a similar way that the hydrogen atom resums photon exchanges at all orders. And the second important thing here is that using the QSIM for the Keplerian motion, we will be able to construct the fundamental building block, which we can then use to eventually calculate observables for Schwarzschild. And hopefully in the last part of the talk, I'll be able to demonstrate it for you. Okay, so just to recap, the golden variable that we want to reproduce is the Laplace observable. And we know how to compute it as the h bar goes to zero limit of a matrix element between solutions of the classical wave equation. And now let me show you how to do this by an example. So let's say I want to compute the azimuthal angle, okay, for relativistic Keplerian motion. Non-relativistic, it's rather simple. Relativistic, it's a little more involved because there's precession, right? So we will get something which is not exactly time periodic. And I haven't seen this done explicitly before. You can kind of indirectly infer it if you know R of t and R of phi, but I haven't seen this done analytically before. So let me remind you what we need to do. We want the Laplace operator, which is going to be the h bar goes to the zero limit of the corresponding matrix element of this operator. And now we just represent it as using spherical harmonics. Note that at this stage, we have to actually compute the full matrix element. We can't like cheat and do WQB now. So WQB was good for the proof. But if we were to use WQB right now, we'd go back to square one. We'd go back to the classical ordinary inverse Laplace transform that we're trying to compute. So we did nothing. So WQB good for proof, not good for using it. So we actually have to compute this matrix element. Now, if you integrate over the YLM part, you just get the normal dipole selection rule in this case, which leaves us with the radial integral. Okay, so we need to integrate two wave functions with this factor. And it's very similar to the integral that you do for a dipole transition. It's not exactly the same, but it's doable. But it's ugly. So this is the result. Usually they don't show it to you in undergrad quantum, but this is the result for a forbidden transition. It's called an appel function. The details of the h bar goes to zero limit are involved, but note that when you take h bar to zero, it always goes in the direction from complicated functions to less complicated functions. It's always a simplification limit. So if f2 is a very complicated function, when I take h bar to zero, there's going to be a lot of arithmetic, but eventually I'm going to get to Bessel and hypergeometric functions, which are like a degree less involved. Okay, so I'm not going to show you the equations, but here's the plot. Okay, so it's the same analytic Laplace observable that's used to compute both the unbound and bound regime, as we saw. And you see that it's precessing, because you see in the bound regime, the cosine phi of t is not periodic. Okay, so this is the full precessing orbit analytically. And I have not seen this formula before. Any questions before I move on? All right. Good. So without getting into too many details, we also computed the electromagnetic field. So let's assume now that I have not just a Coulomb charge. I have Let's assume now that I have a classic electron going on a relativistic Keplerian orbit in the atom. It's accelerating, so it's generating. Yes.
Sorry, can I ask? Sorry, can I ask? So, I mean, I'm just trying to understand the WKB limit that you're taking. So you say it's h bar goes to zero, but usually in solutions of the wave equation, like around the central potential that I'm familiar with, you also take L to infinity. Is that
Yes, that's exactly what
do
I'm doing.
that too? Okay.
Yeah. So here,
Okay.
before I take h bar to 0, I set J, R, L, and M to 1 over h bar, these finite quantities. So now as I take h bar to 0, naturally the quantum numbers go to infinity.
Okay. Okay. I see.
Yep.
Thanks.
Yeah. So yeah, your intuition is completely correct, and it's very important. Good. Okay. So we want to also compute let's say we have a classical Keplerian, relativistic Keplerian electron, and we want to compute at all orders, not just dipole, the electromagnetic field that emits outside. So that's also something that I have not seen analytically ever before, and we managed to do this. So this is in Fourier space or Laplace space, and not in the time domain. But you can see that these are just the Fourier coefficients or the Laplace coefficients, and these are their residuals from numerics. Okay, now the fact that there's little error here is just because we were lazy about the numerics. So there's a 10 to minus 4 error. If we were to be better, then we could systematically reduce this error. So this is an exact calculation. Of course, it depends on, how many, you have sums that you are truncating at a certain point. So you have to take enough terms in the sum that you're truncating. But the bottom line is that using the same methods, we can compute not just the trajectory, but also the emitted field analytically to any to all orders in the coupling. Okay, let's talk some physics. So besides computation, let's take the non-relativistic limit. So now the electron is really doing Keplerian motion like Earth around the sun. So no relativistic effects. And now let's look at the AT radiated over one period by Keplerian electron. And let's compare different kinds of trajectories. So we have in yellow the waveform from a slow circular trajectory. In blue, we have a fast circular trajectory. Green is a slow eccentric, elliptic trajectory, sourcing the electromagnetic waves. And in purple, we have the fast eccentric. So you can see that for the slow trajectories, there's a selection rule that the delta L equals 1, basically the dipole is the only one that contributes. Okay. For slow circular, we have also a selection rule that delta n equals delta L. So you see that we're basically getting just one sine wave. That's the yellow line. Okay. For the fast circular, we don't have the selection rule that delta L equals 1. So not just the dipole contributes, all other transitions contribute. But because of the circularity of the orbit, we do have a selection rule that delta n equals delta L. And as a result, you see that there's basically this blue shape. And similar for the two other trajectories. The interesting thing here is that there's an observer effect because our detector is now, we put it somewhere far away on the x-axis. So there's going to be a Doppler effect between if the source is moving towards or away from the detector. And that creates an asymmetry in the fast orbits, which is visible only in the fast orbits. So you can see in the blue and the purple, the waveform is a little asymmetric, while in the yellow and the green, it's roughly symmetric. Okay. We can also look at the relative importance of different multiples of radiation. So if the source is slow, then the dipole approximation is just perfect. Okay, so you can see that the power that we're radiating in the dipole, which is the blue here, is way more than all the other multiples, no matter where we are in the frequency, in the harmonic in energy. However, if the source is fast, what we see is that as we go to higher energies in the in the Fourier series, the dominant contribution comes from different multiple radiations. Okay, so the lesson to learn here is that you can't just do a dipole computation. Okay, and if we were to compute back reaction from this and self-force, we would and only take the dipole approximation, would be very, very wrong. So we actually need to compute analytically all multiples of the outgoing radiation. And this is a lesson that continues for gravity as well. Okay, so we're nearing the end. And I want to, so far I said a lot about the method and how we applied it for electromagnetism. And for a long time, we kind of did everything, just like prepared our tools for electromagnetism and just kind of blindly trusted that this would work for GR. Okay. And at some point we thought that we were kind of hitting a brick wall because to apply this method, we actually needed to solve the wave equation in a Coulomb background. So to apply it in the Schwarzschild regime, you'd naturally need to solve the wave equation or the Klein-Gordon equation in the background of Schwarzschild. Now, the solutions are known. They're used for black hole perturbation theory. For people, those familiar, it's called like the MST method, Manu, Suzuki, Takasugi. But these are complicated functions. They're very annoying, and I don't know how to compute integrals over them, which is what we need for the method. So for a while, this was kind of like a potential kind of block in the future that I tried not to think too much about. But recently, in our last paper, we had a breakthrough, and we realized that there's a trick that allows us to completely reduce the Schwarzschild computation to the Coulomb computation that we already did. So this is what I want to tell you. So I want to show you that there's no hold up in moving to the gravitational case. Okay, so before I do that, let me just show you something cool. To compute time-dependent geodesic motion in Schwarzschild, we don't actually need the QSM. We do need it to compute the emitted radiation gravitational field, but the motion itself is integrable, and these are ugly, ugly integrals, Jacobi functions and elliptic integrals, but we actually did them and produced these forms. And if you're interested in seeing a bunch of arithmetic, ask me and I'll show you in the backup slides. But now getting serious, we want to apply the QSM for, in the case of Schwarzschild. And there seems to be a holdup in that we need to solve the Klein-Gordon equation in a Schwarzschild background. And the solutions are ugly, ugly confluent Hoyne functions, MST solutions, and all kinds of swear words. Okay. But here's the trick. Okay. In the H bar goes to 0 limit, which is ultimately the limit that we're interested in, all field solutions go over to their WKB form. And the WKB form is, e to the power of the I over H bar, the Hamilton-Jacobi function for Schwarzschild, which is something that's hard to compute, but computable. Let's do the trick. Let us multiply, shamelessly multiply, but by the full field solution for Coulomb, which is what we've been using all this lecture, and divide by the WKB limit of Coulomb. Okay, because we're eventually are interested in the H bar goes to 0 limit, this is effectively like multiplying by 1. We're multiplying by a full solution divided by its WKB form. What we get now is that the wave function, or the radial function for Schwarzschild, is just the Coulomb wave function times the exponential of the difference in the Hamilton-Jacobi actions. And both S Schwarzschild and S Coulomb are analytically computable, and they appear in the backup slides if you're interested. And here comes the physics intuition. The point is that when the small black hole is very, very far from the large black hole, it's very, very far from the Schwarzschild curvature, it actually feels effectively just a Coulomb interaction, just a Newtonian pull on it. Okay, so that means that if I were to plot in the next slide the difference between the two actions, it would actually be small and it would go to a constant. So this is something that I can just expand. I can expand it in R, I can expand it in a PM expansion. So what I'm getting is basically the actual wave function that I need to use to apply the method to Schwarzschild is proportional to the wave function for Coulomb, which I already know how to integrate and use, times a polynomial, some Taylor expansion in R and in G. So this is something I know how to work with. And here's a plot of the difference between the two functions. So it's just a finite phase, okay? Of course, it matters that it changes with R, but it's a small correction which I can now expand in my favorite PM expansion. So the bottom line is that we reduce the computation of Schwarzschild matrix elements and Laplace observables and everything we ever want to do to a sum of known Coulomb ones. And in an upcoming paper, we will compute geodesic motion and first-order gravitational cell force in Schwarzschild analytically to any desired order in G using this method. So, to conclude, first we solved the problem of analytical continuation between bound and unbound orbits for any time-dependent observable in a spherically symmetric conservative system. Then we showed how to exactly compute time-dependent observables for relativistic Keplerian motion by applying our master equation. And finally, what we did is we showed how to reduce the computation of time-dependent observables in Schwarzschild. We haven't done it, but we realized how to reduce it to just a PM sum of known Keplerian computations, which each one of them we already know how to do. So stay tuned for a fully analytical computation of a first-order cell force in Schwarzschild to any desired post-Minkowskian order. Thank you.
Thanks, Ofri. Any questions?
Yeah, I had a question. Could you explain again the WKV limit over there? We take H bar to 0.
Yep.
Maybe you explained it already, but I didn't follow maybe.
No, it's a good question. It's actually at the heart of the method, so it's very good to revisit. Okay, so I'm going to use the words classical and quantum, though the more proper words I should use would be point particle and field solution. But let's think that we're non-relativistic, and we're actually extrapolating from the hydrogen atom, the Keplerian motion, just the ordinary Keplerian motion. What I'm telling you is that if I take literally the hydrogen atom and I compute a matrix element between two orbitals of the hydrogen atom, and now what I do is I say, these are not just like any orbitals. These are orbitals with very, very high quantum numbers. In fact, their quantum numbers go to infinity, but they go to infinity in a specific way to reproduce classical behavior. So I take H bar goes to 0. I take the quantum numbers to infinity, but their product is something with the same dimensions as H bar. So H bar has dimensions of angular momentum. So what I'm going to get is action variables, classical action variables. Okay, what classical action variables do I have? I have JR, which is the radial action. I have L, which is the angular momentum, and I have LZ, which is the angular momentum in the Z direction. So these are classical quantities. This is how I tell the system what to go over to in the classical limit. And what I'm telling you is that if I take the classical limit of hydrogen atom observables, I'm going to reproduce Fourier coefficients of Keplerian orbits. So the actual elliptic motion of Kepler is somehow secretly locked inside the hydrogen atom that we learned in undergrad.
I see. Thank you.
No problem.
Right, more questions. I have a question actually. So, I mean, you mentioned that you think about scattering from the direction of particle physics, but also in particle physics you have bound states. So
That's right.
has this kind of technology been used purely in particle physics, extrapolating between bound states and scattering?
Well, I think that here the classical limit is hardwired into everything that we do. So I would say that okay, so when is it relevant? It's linked to essentially the Econo limit in particle scattering. Okay, so when you do Econo, which means that you have two particles that are kind of grazing each other and going in the same direction, then you can resum and you can pretend that you're in the classical limit. Even if you're doing quantum scattering, it's going to behave like a classical system in a sense. So yeah, these methods and similar methods have been used in the context of Econo resummation. For example, there are papers from the 70s by Itzikson and Zubair and all these people. They were very big on these things.
But then they could be relevant also for like bound states of particles, but not in gravity, just in other particle interactions. That's why.
Well, in the semi-classical limit. So if you have like heavy quark effective theory, yeah, is very much linked to these things.
Mm.
Yep. And in fact, some of these tools, like the reason people wanted to do black hole scattering with particle physics with scattering amplitude started from an analogy with heavy quark effective theory. So yeah.
Okay, more questions?
You want me to show you the fundamental frequency?
Yeah, please.
All right. So let me jump there. Okay, so I'm not going to get into the proof because this is too much, but this is the statement. Okay, take two energies that differ by delta JR units of the radial quantum number or delta L units of the angular quantum number, and take the difference, divide by h bar times the difference in the levels, and you just get the classical fundamental frequency. Here I denoted by epsilon, not by omega, but it's the same thing because this is non-relativistic. I can reproduce the precession, the periastron advance, for example, just from hydrogen atom like eigenstates, eigenenergies. And so the reason it's true is because of Bohr-Sommerfeld quantization, but I'm not going to explain it. What I do want to focus on is this little yellow square here, which is, you can check it at home, and it's very amusing. Take the energy of the hydrogen atom, form this thing, and you get exactly Kepler's third law.
Very cool. Any questions? So actually, one last question. So I'm interested in what happens in Kerr. So you were focusing on Schwarzschild, but is there some problem in principle with doing Kerr, or is it just everything is more
There's any
complicated?
problem? No, I think what we're doing here is the complication is like orthogonal to if it's Schwarzschild or Kerr. Just use Kerr, YLMs.
Wave functions. Yeah.
Yeah.
Spheroidal harmonics. And
exactly. And I think it should just work.
okay. Great. So if there are no further questions, let's stop the recording. But first, let's thank Ofri again. Okay.